All right, chapter 15, capacitive AC circuits. You already know about capacitive DC circuits. What we're going to study this evening is capacitive AC circuits. It's a real game changer, okay? But if you follow the recipe, and there's an easy recipe for success, as a matter of fact, it's all tied up in one formula. If you know the one formula, makes the behavior of a capacitor in an AC circuit totally predictable. After completing this chapter, you're going to be able to describe the phase relationship between current and voltage in a capacitive AC circuit. Determine the capacitive reactance in an AC capacitive circuit. Describe how resistor-capacitor networks can be used for filtering, coupling, and phase shifting. And explain how low-pass and high-pass RC filters operate. Now, capacitors in an AC circuit. AC voltage applied to a capacitor gives the appearance that electrons are flowing in the circuit. Okay? Let me draw a quick circuit here. What kind of a circuit is this? The way you should always start off with is the power source. This is a DC series RC circuit, right? A DC series RC circuit. The fact that it's DC tells you what you're dealing with as far as power. Series tells you whether current's going to be constant, or in a parallel circuit, voltage is going to be constant. RC circuit tells you that you've got resistance and you've got the property of capacitance, right? Now, you guys know a little bit about the circuit, don't you? I hope you know something about this. I get the switch here. I got the switch SW1, switch 1. When I close switch 1, what happens inside this circuit? What happens inside this circuit? Allows current to flow. Where does current flow? Okay, so current just flows through the circuit like this. Let's take a look more here at what's going on right here, okay? This component here is a capacitor. What is a capacitor? Two plates separated by a dielectric material. It's like a battery. But this is a dielectric material. A dielectric material is a fancy way of saying insulator. So let's go back to the circuit here. When I close the switch, does current flow through an insulator? So Mr. Carter was accurate when he said the capacitor begins to charge, right? Let's talk more about that charging. When I'm actually charging the capacitor, the voltage is going from 0 up to 100%, and it takes time to do that. So as the voltage, V sub C, voltage of the capacitor is increasing, what's the voltage of the resistor doing? Decreasing. And where is it starting off at? At 100%, and it's going to 0%. So it's coming down like this. Voltage resistor. When we're charging the capacitor, is current flowing in this circuit? When we're charging this capacitor, is current flowing in this circuit? Absolutely. Absolutely. Because all of those electrons are going basically to the negative charge is on this plate here and positive on this plate here. So if I've got a voltage that's increasing here, current is increasing. Current flow goes from 0 to, or actually it goes from 100% to 0% while that capacitor is charging. When I first close this switch, current is at 100% in this circuit. And what kind of a circuit is this? Series. So if I've got current flowing here in the circuit, do I have that same amount of current flowing here? Why? Thank you. And what's the most important thing you need to know about a series circuit? Current is constant in the series circuit. So if I've got current flowing here in a circuit, out of the negative terminal of the battery, I've got current flowing here the same amount. Do I have that same amount making a 90-degree turn here at the speed of light? Absolutely. Do I have that same amount of current flowing here? Here, 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 here? Everywhere. Because current is constant in the series circuit. Can you dig what I'm selling? Does that make sense to you? Okay. So, back to the statement here. Gives the appearance that electrons are flowing in the circuit. Back when we studied this last week, did it have the appearance that current was flowing in a circuit? None of you questioned me on this last week. I didn't bring it up because I thought I didn't want to bring it up last week, but I kind of got to bring it up this week. Last week when we were charging this capacitor, was current flowing in the circuit to charge this capacitor? Absolutely. Was current flowing in the series circuit? Yes, it was. Can current flow through a dielectric material? No, it can't. But can current flow to build up an electrostatic charge across two plates? Yes, it can. And that's the current that's flowing. When this capacitor gets to 100%, current in the circuit goes to 0%. Does that make sense? Very, very important concept. And you got to believe me with this, okay? Especially this week with this chapter. So it gives the appearance that electrons are flowing in the circuit. Are electrons really flowing in the circuit? Yes. Are they flowing through the capacitor? No. Am I building up a difference in potential across the plates in the form of an electrostatic field? Yes. And in order for me to do that, there must have been current flow, because what is the plate? A giant parking lot for electrons. Now, check this out. This is funny. I think it's funny. Current and voltage do not flow in phase with each other. They're 90 degrees out of phase. Current leads voltage. Current leads voltage. Is this a new concept to you? Is this something that I'm just first presenting to you in this chapter? I'm saying it like this for the first time in this chapter, but actually last week you were looking at it. The voltage across the capacitor is increasing. The voltage across the I hate that. I don't like that. I'm going to erase that and redraw it. Come on, look at that freaking thing. I'm not going to like this one either. Yeah. Voltage of the resistor. Voltage of the resistor starts out at 100% and then it decreases to 0. Current starts out at 100% and it goes to 0. Why does current go to 0? The capacitor gets fully charged. So, I've got colors up here. This VR is blue. Is in red. Total current is in red. So as the voltage of the capacitor increases, the current through the circuit decreases. Were these two things, for lack of a better term, in phase last week? Were these in phase last week? No. This week's lecture, this is what you were looking at. So things were out of phase last week, you just didn't know they were out of phase. Here, this week, in applying AC to it, we're going to have phase shift perpetually. Now, when you're dealing with capacitive circuits, like this one, there's a word I want you to remember. And I want you to put this word on your scrap paper. Anytime you take a quiz, an examination, anything like that. The word is ice. Ice. The reason this word is so important, in a capacitive circuit, letter C, in a capacitive circuit, current leads voltage by 90 degrees. Current leads voltage by 90 degrees. By leading, we mean goes to 100%, and then voltage is going to follow that by 90 degrees. They're going to be offset by 90. Check this out. If I actually kind of filled this out, made it like into a sine wave, if I'm at the peak value right here, this means that what? I'm like at 90 degrees right here, and this would be like 0 degrees or 180 degrees. Do you agree with that? And like if this here, this is at the start of a waveform, this would be at 0 degrees, and this would be at 90 degrees. So when the voltage of the capacitor is at 0 degrees, where is the voltage across the resistor? At 90. When the voltage across the resistor is at 180, where's the voltage of the capacitor? How many degrees of phase? 90. In a capacitive circuit, the behavior of current leads voltage. Does that make sense? Now, if we were to plot this out with an AC sine wave applied to it, this is what it would look like. Voltage, because actually, let's go back. Let's dissect this. This is actually kind of cool. So I'm feeling so crappy tonight because I love this freaking lecture, man. I live for this lecture. Okay? Voltage or current is at 100%. You see that right there? Isn't that like this right here? And when this is right here, voltage is right here, that's like this right here. When I go up from 0 to maximum peak value, 0 to maximum peak value, my current flow goes to 0. Here, when the capacitor discharges, it's going to discharge in the opposite direction of what originally charged it, so my current now is going to flow backwards. It's going to flow backwards. Here, now my alternating current, AC, goes from 180 degrees to 270. That means current goes from 100% to 0%. Why? Because the capacitor gets fully charged here, but in the opposite direction. Here the capacitor discharges back to 0, inducing current flow back into the circuit in the opposite direction. So the way that this works, check this out, I don't think anybody. It's like, this is what's, and voltage is always 90 degrees behind current. Why is it always 90 degrees of phase shift in a capacitive AC circuit? It's an easy answer. Why is it always 90 degrees? Why isn't it 87 degrees? Why isn't it 113 degrees? Why is it 90 degrees of phase shift in a capacitive AC circuit? And you're looking at the answer. Do I look left or right? You're looking at the answer. Why is it 90? Why isn't it 87? Okay. So what's an AC sinusoidal waveform doing every 90 degrees? It's doing that every 180 degrees. What's it doing every 90 degrees?
Rising or?
It's changing direction. For the first 90, it's rising. For the second 90, it's falling. For the next 90, it's increasing, but in the opposite direction. And then for the last 90, it's going back to 0. So what is an AC waveform constantly doing? Constantly changing, and every 90 degrees, it changes and reverses itself. well, every 180 degrees it reverses itself, but it changes the direction. First it's decreasing, then it's increasing negative alternation, then it's decreasing back to 0, and then it just repeats itself. In a pure capacitive circuit, current leads voltage by 90 degrees, period, end of story. Always 90 degrees, purely capacitive. How much phase shift is there in a purely resistive circuit? This is a review question, by the way, last chapter. How much phase shift is there in a resistive circuit? 0. How much phase shift is there in a purely capacitive circuit? 90. And what leads what? Current leads voltage. And if you can't remember that, and I can't remember it, that's why I remember this crap, get it on your scrap paper, ICE. In a capacitive circuit, current leads voltage. By how much? Always 90 degrees. Make sense? Now, how many of you would dig calculating out time constants for something that's constantly changing? Any takers? Okay. The forefathers of electronics basically figured this out, that they would go insane if they had to calculate out time constants for something with AC. So instead, what they came up with is they wanted to come up with a value that would show how a capacitor reacted to a different frequency of AC. So what they did is they put this capacitor into a category of components that's called a reactive component, because it reacts differently. It reacts differently. Because at a low frequency, this capacitor is going to be able to charge a lot quicker, right? At a low frequency, there's more time. At a high frequency, this capacitor is going to have a tough time getting up to that 100%, because as soon as it's on its way up, next thing you know, it's reversing itself. Because a higher frequency means more alternations per second. Plain and simple. So it's going to vary. It's going to vary with frequency. What they came up with is, and this is solid gold, man. This is choice. This is primo that they did this. They came up with something that's called, this is a typo here, this should say capacitive reactance. Capacitive reactance. Capacitive reactance is the opposition that a capacitor offers to the applied AC voltage. And we abbreviate it by what we call X sub C. X sub C, capacitive reactance. You want the good news? You want the really good news? I'll give you the good news. It's measured in ohms. Why is that such good news? Because all of you in this room are used to working with ohms. Can you add up ohms in series for me? Can you add up ohms in parallel for me? Can you add up ohms in complex circuits for me? Well, this formula is all you freaking need. It's all you need. If you apply this formula to an AC capacitor in a circuit like this, it's going to show you how much ohms of reactance it has. And then you can use the same math that you used at the beginning of the quarter analyzing those simple series circuits that I gave you to analyze. The exact same thing. So quite frankly, this whole lecture, it's a waste of time. There's only one thing in this lecture that has any value. And it's this formula right here. It's this formula right here. The formula is X sub C, capacitive reactance. That's how you say it, capacitive reactance, X sub C, is equal to 1 over 2 pi FC. I just changed the F and C. No, literally, I just changed the F and C to red. They were green. Change the F and C. Why is that so humorous? Guys, gutters. Mine's in the gutters. The reason I changed the F and C is that the F and C are the only variables in this formula. They're the only thing that's ever going to change. let's dissect this formula. This here, number 1, is the first number on the number line. It's number 1. It means not 2, but 1. This line right here means 1 divided by the product of the number 2, which is the second number in the number line. It means not 1, but 2. This is where we kind of get wacky. Bear with me though, works out okay in the end. This here is pi. Pi. Pi is a mathematical constant that deals with what? That's the number, 3.14. Don't go beyond that. There's a reason for that. I'll tell you, 3.14. We used to do that in high school. Before bullying used to be in vogue. Bullying used to be cool. So we used to go around. So yeah, you know, find the nerds. And be like, you know, it's like, what's pi? You know, they 3.14. Whoever knew it back the furthest past the decimal point would like work over. You know, it's like, it's kind of funny now because they own like, you know, all these like Fortune 500 companies and stuff. I get back to my high school reunion and stuff. Remember me? You beat the crap out of me. I'm sorry, dude. It seemed like the right thing to do. What is pi? What is pi? Pi is the radius of a circle. So what this is saying is we not only want to deal with 1 pi, we want to deal with 2 pi. Why are we dealing with 2 pi, not 1 pi? The whole circle. But what whole circle are we dealing with?
Peak to peak.
Peak to peak. So we're dealing with not 1 alternation, we're dealing with 2 alternations. The positive and the negative, or the magnetic field, the generator that originally created the sinusoidal waveform. Make sense? Mr. Carter, question?
Why don't they just put 6.28 instead of 2?
That's a good question. We could do this 2 different ways. Very, very good question. Here, we let you use a scientific calculator. And the true formula is pi. When I was in school, 3.18 because I had to memorize pi. I was not able, I had to use a calculator that was just like this when they let me use a calculator. And actually before that, the nuns wouldn't even let me use a calculator. But what happens if the battery dies? I don't do math that day. You know, go see the priest. You know, and Mr. and Mrs. Grenick were there, and it was an ugly situation. I'm like, seriously, if my battery dies, I'm not going to do math that day. I'll get a new battery, and I'll do math the next day. I mean, what's the problem? Whacking me. Good thing. Say it's a good thing we went on a metric system because had the nuns been using meter sticks as opposed to yardsticks, I probably wouldn't be here today because there are a couple times that you just. Use scientific calculators. With that comes a burden of you using the most accurate number. So use pi. It's a mathematical constant that's programmed in. You got a pi key. You use it. It's going to give you the most accurate answer. So back to the F and C. F stands for frequency measured in hertz. F is frequency measured in hertz. C stands for capacitance measured in farad. So when you take 2 times pi times the frequency times the capacitance, and then take the reciprocal of that, 1 over, that shows you what the capacitive reactance is measured in ohms. It's that simple. So one of the things that I want to show you with this formula, and I want you to, hopefully the way I'm presenting this to you, you appreciate this formula more than just the formula. If you know the formula, you know what it's doing, it's a lot easier to follow along. With frequency, if I increase the frequency, what am I going to do to my capacitive reactance? It's always easier. This here is sitting underneath this line. So whatever I do down here, and I'm not going to change the number 2, because that's like the second number in the number line. It means not 1, but 2. Pi, we're definitely, okay? That's actually the safety deposit box at an undisclosed location. I have a Hollywood screenplay that I wrote the day pi changed, you know? And it was like some scientist, you know, he's performing his calculation. So, oh my God, oh no! You know, wheels are no longer round, and, you know, the earth has shifted off its axis, and, you know, hopefully this teaching gig continues, because if not, I'm gonna have to break out my screenplay and try to have it done into a full motion picture, you know? The day pi changed. Pi's not gonna change, it's a mathematical constant. So these two numbers are not gonna change. If f increases, x sub c is going to decrease. If c increases, x sub c is going to decrease. If f or c decreases, x sub c is going to increase. We call this an inverse proportional relationship. So if I ask you on a test, frequency and capacitive reactance is A, a direct proportional relationship, B, an inverse proportional relationship, C, none of the above, D, all of the above, you're going to want to get this inverse proportional relationship. Right. Answer B, inverse proportional relationship. Does that make sense? That's the formula. Once you do that and you implement this formula, I could put these components in series and parallel, whatever, it's all good. This formula drives this entire chapter. Pi is the mathematical constant, 3.14. Don't use that though, use the pi key in your calculator. F, frequency in hertz, C, capacitance in farads. So you got to be real careful how you enter these. Because typically with capacitors, are we going to be dealing with farads? What are we typically going to be dealing with? Microfarads, picofarads, millimicrofarads, nanofarads. So it's going to be many places past the decimal point. That's why, remember when I said at the beginning of this quarter, how important it was to deal with engineering notation? Because now, I mean, check out just this formula. 2 times pi, the mathematical constant, times frequency, probably going to be in kilohertz or megahertz or gigahertz, times 10 to the third, 10 to the sixth, 10 to the ninth, times 10 to the negative sixth, negative ninth, negative 12th. It's a huge number to input this. You try using old school, 2 times 3.14 times 3,0,0,0,0,0. No, I counted wrong. You know, you're going to mess up. So you want to be able to enter this in engineering notation. This is where the rubber hits the road. This is why it's so important that you develop the skills in entering those numbers in your calculator. Capacitive reactance is a function of the frequency of the applied AC voltage of the capacitance. Meaning when this changes, these change, it affects this directly or inversely. Applications of these circuits can be used alone or combined with resistors to form RC networks. Used for filtering phase shift circuits, decoupling phase shift circuits, DC blocking phase shift circuits, and coupling phase shift circuits. Also used for what's called a filter. A filter, this is a good one, you can go home tonight. What'd you learn over at that technical college tonight? We spoke of discrimination. Because that's what we're talking about here. A filter is a circuit that discriminates among frequencies. Your $1 million word for tonight is attenuating, which is the opposite of amplifying. You've all heard of amplifying before. An amplifier, you put in a small signal, you get out a big signal. Sometimes we want to attenuate a signal. Put in a big, get out a small signal. Discriminating, a filter is like a coffee filter. What's a coffee filter do? Filters out the grounds and allows the coffee fluid to pass, but it holds the grounds behind. That's what an electronic filter does. It keeps the bad stuff out and it allows the good stuff, the good frequencies to pass. What's that? That would be using it as a blocking circuit if we're using a capacitor to block the DC but allow the AC to pass. Here we're simply talking about allowing some frequencies to pass while others were. most common types are the low-pass filter and high-pass filter. Probably the easiest way of talking about these two is for me to show it to you. I'm going to keep the circuit, part of the circuit. So I'm going to change this power source here. We're going to keep the rest. And I'm doing that for a very specific reason. I'm going to leave it for it as well. Okay? What I'm going to do is I'm going to change my circuit to an AC. This is what kind of a circuit? AC series RC circuit. You agree? Now, I've got really two different combinations of components that I could measure, three different combinations I could measure across. I could measure at point A, I could measure at point B, and I could measure at point C. I could measure the voltage across the, what would I be measuring here? The resistor, the capacitor, which is total. Do you agree with me? Three different combinations here. Okay. So, since I'm applying AC to this circuit, what I'm going to do, and I'm going to start doing this from this point on for the rest of the quarter, I'm going to start showing you these XY plots. My x-axis, I'm going to be depicting frequency. Okay? So this is a low frequency, and this is a high frequency. And this is a frequency that's just right. A medium frequency. Make sense? Okay, so I'm looking at frequency here. This is going to be amplitude. This is 0 amplitude. This is 100% amplitude, which is going to be a measurement of voltage. Okay? So what I'm going to do to this input is I am going to put in a variety of different frequencies and see how this behaves itself. If I put in a low frequency at 100% amplitude, when I put a low frequency into this circuit, what effect is that going to have on capacitive reactance? It's going to increase it. It's going to increase it. So the value of reactance of this capacitor is going to be extremely high. When I put a low frequency into this resistor, what effect is a low frequency going to have on this resistor? What's that? Daniel? It's not going to have any effect on it because the resistor is purely resistive. So frequency is not going to have an effect on this. But when I put a low frequency this, the value of, what property we measure here that's so important to us? Reactance. How do we abbreviate that? X sub C is going to be extremely high. And what's this measuring? Ohms. So this is going to be a huge value here at a low frequency. This is just going to be whatever value it is. So when I put in, let's do a mini XY plot right here. Let's do a mini XY plot here. This is frequency, this is amplitude. Let's do the same thing across A and B. This is frequency, this is amplitude. At a low frequency, where am I going to get the biggest voltage drop in this circuit? Across the capacitor, because this has a high value of XC. So how would I plot out at a low frequency AC voltage drop? Does that make sense? What kind of a circuit is this? Never forget that. Never forget that. This is still I got a big voltage drop here, what's my voltage drop across my resistor going to be? Because a series circuit is also known as a voltage divider. So if I got a big voltage here, what's my voltage across my resistor going to be? It's going to be low. Do you agree? Am I baffling any of you? Hopefully not. It's all straightforward. This is all stuff that we've studied. If I put in a high frequency now, high frequency at that same amplitude, value of capacitance reactance is going to be low. And if it's low, it's measured in ohms. So I'm going to have a low value of ohms right here. Low X sub C. If this is a low value of X sub C, am I going to get a big voltage drop across this or a high voltage drop across it? Low voltage drop. So when I measure between point B and C, I'm going to see a very small voltage drop in this capacitor. So if I'm plotting that out, this is a high frequency, low amplitude is going to look like. It's going to look like that right there. If I'm getting a small voltage drop across the capacitor, what am I getting across the resistor? I'm going to get a high voltage drop across the resistor because it's a voltage divider. It's a series circuit. Make sense? Okay. This is where it gets fun. Let's put in a medium frequency. Medium frequency at that same amplitude. This amplitude here is going to be kept constant. I want to make sure that I put in the exact same voltage into this circuit and that I check for each low frequency, medium frequency, and high frequency. So if I put in a medium frequency, what value of X sub C am I going to get? I'm going to get medium. I'm going to get a medium value of X sub C, which means measured in ohms, I'm going to get some voltage drop across it. Okay? So let's just say I get a medium amount of voltage drop across it. If I get a medium voltage drop across my capacitor, where's the remaining voltage drop going to be? It's going to be across the resistor, so that's going to be right here. If I plotted this out, if I actually swept this input by hooking it up to a sweep generator where I put in low and then whoop, I go all the way high and I keep doing this, what I would What I just did is I created not only a low pass filter, but a high pass filter. And the difference between a low pass filter and a high pass filter is what? Where I connect my output. It's that simple. Both low pass filter and high pass filter are both examples of series, AC series, RC circuits. For a pass filter, do you see how I'm passing that high frequency? Or, excuse me, low pass, what am I saying? Low pass filter, see how I'm passing the low frequency? Where do I have my output connected to? Across my capacitor. Across my capacitor, what's another way of saying across my capacitor? In what configuration with my capacitor? Parallel, thank you. And that's key. You want to pass this quiz? Remember that. This is a parallel capacitor. Because what's constant in a parallel circuit? Voltage. That's what we're trying to harness here. So this is parallel. Is this a... Yes, it is. But we're connecting in parallel to the parallel capacitor to make sure we get the same voltage across it. When you connect in parallel with the capacitor, we call that a low pass filter. If I connect in parallel with the resistor, I call that a high pass filter. So I put a low frequency into this circuit right here. If I'm connected here to this circuit as a high pass filter, I put in a low frequency. That low frequency is not going to make it out. Only the high frequencies are. Some of you have probably heard of like crossovers before for speakers. That's exactly what you do. It's exactly what we do. Use a resistor and a capacitor, and what you do is what would we be feeding here? What would be connecting across the capacitor here? What kind of a speaker? What kind of a speaker would we connecting here across in parallel with our capacitor? Subwoofer. Subwoofer, or a bass speaker. Because what do we want to feed that subwoofer or that bass speaker? Low frequency. You feed it high frequency, it can't even do anything with that stuff. It's not designed to do anything with that stuff. What would we be feeding to this here? Tweeter, or high frequency. And achieving this point, this crossover point between the two, because I've got colored pens. Finding this point right here is critical. Having a speaker that could handle, and then pairing it with a speaker that can handle these frequencies is key. In some cases, you have a subwoofer, you have a bass speaker, you have a mid-range, you have a tweeter. But the key is, like a traffic cop, directing all the frequencies to the right speaker. Because if you have a subwoofer, these high frequencies, you can't even do anything with it. You're wasting energy. This is where people that screw around with audio, there should be a license that you got to get before you can screw around with audio. I guess anybody could get a big amplifier and speakers and hook it up and make sound come out of it. But I tell you what, when you do it right, stuff begins to pop, stuff begins to happen. It's like, whoa, this really sounds freaking impressive, because they got it dialed in. What you're studying right now is how you dial it in. Does that make sense? This whole chapter is one formula, and if you embrace that formula, everything else that I showed you, series circuit, series RC circuit, AC series RC circuit. You should be comfortable with that. Current's constant in the series circuit. The series circuit is also known as a voltage divider. If you want to harness the voltage that's being developed, you need to connect it in parallel with the output, or connect the load to the parallel component. This is the parallel cap, this is the parallel resistor. Do not deceive me, or you'll get it wrong in the quiz. And then you'll be challenging the man, and the man will have no sympathy.
So a subwoofer would be hooked up between branch C and B, basically?
Yep. What I done draw it on the board here, this is my artist depiction, you kind of get the gist. This is actually what it would look like. Not this is the projector coming on. Got my main man back there taking notes on this, trying to draw it. sRGB. This is actually what it would look like. And this is that 100% value. And this is that 0% value. The critical cutoff frequency is going to be this right here, 70.7% of the output. So whatever this is, when we get to 70.7%, everything below this is going to get rejected. Everything above this is going to get passed. So we could call this a low frequency pass filter. Or we could also call this a high frequency reject filter. It depends on what colored pill you're taking, okay? What way you want to look at it. Some companies refer to this as a low pass filter. Some refer to this as a high frequency reject filter. They're both synonymous. They both do the same thing. And to figure out exactly what this cutoff frequency is when you get to 70.7%, right at this point. And there's some ways we'll talk about in the future how to move this cutoff frequency. High pass filter we talked about already. High pass filter, we're doing what? We're connecting it to the parallel resistor. It consists of a capacitor and a resistor in series with each other. All of these circuits consist of capacitors and resistors in series with each other. This is what's called a decoupling network. What is this? This is a good one. What's the first thing I want you to pay attention to? Your sources. This is an AC-DC series RC circuit. Yep, absolutely. Absolutely. Because this is used, that typically DC is used to turn on semiconductor devices inside circuits, and AC represents the signal, the intelligence of what you're trying to amplify. So in most pieces of equipment, you're going to have AC and DC together. Sometimes you want to pull that DC off and let the AC just go on its way. This is where you're going to use a decoupling network. And the way that this works is real simple. You all agree that this is a DC-AC series RC circuit, right? Well, what's the DC going to do here? The DC is going to do what in this circuit? It's going to charge the capacitor and it's going to stop. Where's the capacitor going to stop charging at? What value? After 5 time constants, where's this capacitor going to stop charging at?
9.3%.
It's going to basically equal the DC value here. So if I connect an output in parallel to this capacitor, what am I measuring at the output? The DC value. What's happening to the AC value? The AC is just going to zip right through the circuit. It's going to go right through that cap. Not an issue. Not an issue. So a decoupling network is pulling off the DC and allowing the AC to pass.
Why do you even need AC in there though?
AC is going to be the signal. There might be something further down the stream here. This is just a simplified illustration of it. We're going to let the AC pass, but we're going to block that DC. This is a coupling network. This allows the AC signal to pass while attenuating or eliminating the DC signal. What do we have here? It's a series DC-AC series RC circuit, same exact circuit. How are we connected here in the circuit? How are we connected here? We're connected where we're taking the output to the parallel resistor. Because what's happening? The DC here is getting what? Blocked by this capacitor. What's the AC doing? Flowing through the capacitor, and as it flows through, does AC generate a voltage drop as it flows through a resistor? What was the second chapter we did? See, you guys are deceiving me already. What's the last chapter we did? AC series circuits. When AC voltage encounters a resistive circuit, does it create a voltage drop? Absolutely. What are we connecting to here? The parallel resistor. So we're going to measure the AC voltage drop established as the AC signal develops a voltage drop across the parallel resistor. Make sense? This is called coupling. Pulling the AC off, allowing the DC to be blocked. Another thing that we could do is phase shift. How much phase shift do we get with a capacitor? 90 degrees. How much do we get with a resistor? 0. So what kind of a circuit is this? And I'm glad this is drawn differently. This is a series RC circuit. It's a series RC circuit. So what we say here is typically when we have a capacitor and a resistor, 90 degrees of phase shift here, 0 degrees of phase shift here. In this circuit, and generally when the circuit's engineered properly, we could get about 60 degrees of phase shift out of this entire circuit. 90 if it was a pure capacitor, 0 if it was a pure resistor. When we put the two together, we say about 60 degrees of phase shift here. So my output here will be shifted in phase by 60 degrees. If it's shifted in phase in 60 degrees here, right, 60 degrees here, 60 here, 60 here, 60 here, what have I just done? 180 degrees of phase shift. 180 degrees of phase shift. Whatever I put in here is going to come out 180 degrees out of phase out of this circuit. And it doesn't matter. I could also get the 60 here, and 60 here. 60 plus 60 plus 60 gives me 180 degrees phase shift. So that's how I also use a series RC circuit. All of these circuits are nothing more than what? Series RC circuits. Filters, decoupling, coupling, and phase shift. How do I do that? With a series RC circuit. Make sense? Kind of a cool circuit. Really are. In summary, AC voltage applied to a capacitor, appearance of current flow. Current flow is represented by the charging and recharging of a capacitor, giving the appearance that current's flowing through it. Current applied voltage 90 degrees out of phase. Capacitive reactance measured in X sub C, represented in X sub C is measured in ohms. The formula, this whole chapter, right there, X sub C equals 1 over 2 pi FC. RC circuits are used for filtering, coupling, decoupling, and phase shift. Low pass filter, we take our output across the parallel capacitor. High pass filter, we take our output across the parallel resistor. We talked about coupling and decoupling circuits. Any questions? Is this good stuff? Are you guys understanding why the beginning of this quarter was so critical on these chapters? Took, what's a goofy class I took? Well, English. Some high school English was kind of goofy. I remember this one thing, we had to write poems. You know, we had to write like sonnets, and we had to one of them was limericks. I was really good at the limericks, although that got me sent to the principal's office as well. But you know, much to my wife's dismay, that I wrote a poem was in freaking high school. I don't like write poetry. So you know what? I took the hit in that class and said, you know what? I'm not going to do this because this sucks. This is stupid. I'm not going to write any poems. Well, you're going to lose X% of your grade. Okay? And I kind of know it. Right? And it didn't affect my life. I think my life turned out okay. Right? Electronics is different. If you did not pay attention to series circuits, you're dead in the water right now. If you didn't pay attention to how to add up resistance in series, you're dead in the water. If you didn't understand the importance of Ohm's law, Kirchhoff's law, Watt's law, you're dead in the water now. Because we keep coming back to all of those pieces, and my assumption is that you know all of those pieces. And if you do know those pieces, you don't. Pickle. And I suspect most of you have a familiarity with what we're doing, so practice is going to increase the level of perfection with these circuits. But I'm going to be brutally honest with you. The only thing I introduced you to tonight that you have not seen before is this formula right here. This whole notion about phase shift, I mean, don't these look like the capacitive curves? You just didn't look at it that way before. Now, I want you to look at it that way. So the only thing new tonight is this formula. Any questions? All right, that's all I got, folks. Appreciate it. Have a good one.